Hi, I'm Candace. Again, I'm the product marketing manager here at RBR. And today we're going to talk about how to select the right CTD. We're going to talk about some technical considerations. So particularly about the features of a CTD that you should think about. Some other physical considerations, which are some of them are still technical, but you'll see what I mean by those. And then extra considerations, which I didn't really know what to call them. It's other extra. It's not the technical and the environmental. It's more bigger picture things. I'm going to show you like a whole bunch of pictures very soon about how to deploy a CTD in the chat feature, in the chat part. If you want to throw in like the coolest way you've ever seen a CTD deployed, I think I would find that very interesting. So that would be really awesome. I'm going to show you a whole series of images about 12 different types of deployments. So again, if you want to share like a cool or odd deployment, that would be really fun. And the motivation behind this was I was a salesperson at RBR for quite a while, and being in sales, a big part of my job was actually coming up with recommending to users how to pick a CTD. So a lot of that stems from the types of questions that I would ask somebody about their deployment or about their environment that they were deploying in, to actually be able to give them a recommendation for an instrument that will work and get the data that they need for their project to be successful. So that's really where the motivation from this stems from. Okay, so the big question, I think the most important question here is, how are you planning to deploy the CTD? So typically when people come to us, they have an idea about a research program or something they'd like to try or a project in mind. So typically it's usually an easy question to answer. And now I'm just going to show you a bunch of examples. So this is the first thing you should think about when deciding how to pick a CTD, is how are you planning on deploying it? These folks are deploying it through ICE in a profiling application. So that's one way. This is a picture from NOAA where a profiling float is being chucked out of the back of a plane to before a hurricane to do profiles. So that is a very different way to deploy a CTD, because there's a CTD on this float. This is an observation platform here at Cove. That's where I'm based here in Halifax. And so this is it's an observation platform. It stays at one location on the bottom. Other people call these like landers. In this particular case, this is a cabled one. So it's a real-time observation system. So again, a little bit different than the other ways that we've seen deployments so far. This is a pretty common one. I would call this a small boat deployment. So you can see they're very close to the water. They're just putting a CTD over the side and into the water. So this is something to think about, like, are you doing it from small boats and Zodiacs? Are you putting CTDs on Argo floats? Is that how you want to deploy your CTD? In this particular case, these folks are deploying through ICE, like the first image, but also with real-time data being sent up to the surface because it's being frozen in. So this is, again, an interesting one. Or are you deploying it from a cage, off a boat? Again, there's different ways. This is a glider, and there's also a CTD on this glider. So again, that's a different way of deploying than, say, using putting it through ICE. Are you going to be putting it on a platform, like a profiling platform, like this image? This is a water walker. It's a platform that moves up and down the water column and takes a profile on the way up. So this is a deployment. These photos are RBR photos now. Are you deploying it so we can see a CTD down here, like on a rosette from a ship? That's another way you can deploy CTDs. That's a pretty common one, just like from a small boat. This is our research scientist, Matt Dever, during his time at Hui, deploying a CTD from a winch. So that's another way of deploying a CTD. And finally, a very common way is deploying CTDs on a mooring line. So this is somebody setting up a mooring line. You can see a few CTDs on here. So again, if there are any deployment types that I missed or that you've seen done or that are of interest to you, throw them into the chat. So really, that was many, many different ways of deploying a CTD. But here at RBR, and I think in most places, we really would define those as 3 different applications. And I've said the word a few times of profiling. So just for everyone's benefit, I know this is probably preaching to the choir, but profiling really usually means you're going out some way onto the water, and you're doing a profile. So you're getting from, say, the surface down to a particular depth and back up of CTD information to get temperature, salinity, density, depth. So these are all kind of how we think of it at RBR, the same sort of application. So they're all profiling. So we saw the example at the very start through ice. So it's like a day trip. You're just going out, doing a profile, moving along. A small boat or Zodiac, again, maybe you're doing a whole series of stops. When you put it in a cage, typically you're deploying it. Often cages are used on bigger vessels so that as it's going down, it's not kind of smacking on the side. A wire walker, because it's doing this like clean profile on the way up, that is a profiling application. And typically from a rosette, so that's a very common big ship deployment that, you know, the rosette is going down, you're getting a clean profile on the way down. And then on a winch, again, a nice clean profile on the way down. It could be, you know, a lot of these are in conjunction with something else. So, you know, if it's on a rosette, you're really doing it on a large ship. Moored CTD observations are actually a little bit different. Like the sensor technology can be the same, but it's a different kind of measurement in my mind, in the sense of you're putting the CTD at one particular location and getting a time series of data instead of a profile through depth. So here, this is where the observation platform, the Salamaris that I just showed you earlier from Cove, again, through ice. So the folks who were doing the long-term more deployment through the ice, those instruments are never going to come back. So they have to send the data in real time. And, you know, one, again, of the most simple or the most common ways of deploying a CTD is on a mooring line, or it's typically many CTDs on one mooring line or on a buoy. And then integrations. So integrations, I'll go into it a little bit more later, but essentially we saw 3 in those quick series, like deploying a float from a plane. So there's a CTD on the float, an Argo float, which is a program, an international program of profiling floats, or on a glider. So those are integrating CTDs into platforms, whereas the profiling and the more examples that I showed you, the CTD itself is sort of the platform itself to collect all the data. Okay. At RBR, our CTDs are designed with the purpose. So the purpose is if it's profiling, if it's moored, or if it's an integration. So if you have a profiling CTD, putting it on a mooring line might not be the best. If you have a CTD that was specifically meant for being moored, it might not be super easy to add it onto a float. So I'm putting this out there as a PSA, like really use the CTD for the original intended purpose. So like if you are calling up and you know I'm going to be in the Antarctic and I want to deploy it through an ice hole, et cetera, et cetera, et cetera. I want all these features and functions to it. And then you're trying to deploy in a different type of situation, just like call up your sales rep or support and just ask, you know, is it possible to use it in a different way? Because they are very much designed with purpose in mind. So when that's sort of the beginning. When you're getting or looking for a profiling CTD, these are things that you should think about from my opinion. Again, you can, you might have different ideas. Oh, and KJ, I haven't asked you, sorry. We're also going to do a poll. I should have said that at the beginning. There's going to be a poll about how, there's just 2 questions on the poll. Keith will launch it. So I'm going to go through what I think are the most important things to think about when you're buying a CTD or getting a CTD. And there are other things that I might miss. So it'd be really interesting to hear your thoughts about what you consider to be important when picking a CTD. So a profiling CTD, the very first thing I like to think about is capturing the structure. And by that, I mean the dynamics, or if there's, you know, stratification, whatever like that. I'm a physical oceanographer by training. So I think about that piece. Like, can I see the thing I'm trying to see? Can I do the science really? So for a profile, you really want to be able to capture the structure. So again, for probably preaching to the choir here, this is a super simple example of a temperature profile, salinity profile, and a density profile. And here you can see the thermocline, the halocline, and the pycnocline. And the reason that profiling CTDs needs fast sampling, so capturing many measurements every second, so sub-second sampling, and fast responding sensors, so sensors that are going to respond very quickly, is typically because of these features, the thermocline, the halocline, and the pycnocline, because you want to sample fast to capture this fast change. If you're only sampling once a minute, you might miss this whole feature. So you might get a plot here and then here, you're not really seeing where the thermocline is. So you really want to be able to capture that structure. We use Wi-Fi, but having a way to check that you actually got the feature that you were interested in is a little bit reassuring for me. So like you're going out for the whole day, you're going to do this thing. And is there a quick way just for a sanity check to make sure, did I get the data? Did I capture this front that I was trying to find? Did I see the thermocline? Did I hit the bottom? You know, often we're doing these profiles in, you know, again, we're usually doing it to answer a science question. So, you know, if you're trying to get all the way to the bottom, or you're trying to go through, you know, the pycnocline to see, are there, you know, with a fluorometer to see if there's a chlorophyll maximum there, all those things, it's just really nice to be able to check some way quickly that you got the data, right? And finally, one thing I think about a lot is, you know, will the CTD last me for the day? Will I have to change batteries out like in a Zodiac with the like the Zodiac we saw earlier, like filled with people? Like, is that going to be doable or easy? So if you are doing fast sampling, like 8 Hertz, is there enough memory on the CTD without having to like pull out my computer and download it? Is there enough battery to last me for the day? Or maybe I'm going out on a cruise and I'm going to be out there for a couple of weeks. So really it's like, are the things, will the instrument actually collect enough data? So really, like visually, if you think about collecting data from a 16 Hertz versus a 2 Hertz perspective, if you have a meter a second fall rate on the CTD, that's the difference in 1 meter of water of getting, you know, 16 data points or 2. So again, when we think about these physical features in the water column, like the thermocline, the oclines, if you're sampling faster, you're going to have a better chance of capturing those features. So, you know, having 16 data points versus 2, you're much more likely to see, you know, that data and have that high resolution data. So that's just a particular example of, you know, how that looks. Okay, so for more CTDs, again, I have 3 things I like to think about. The first is related to sort of the sampling rate, you know, I call that analogous to the profiling, is the deployment length. So it needs to last for the entire deployment. And moored CTDs, I usually talk to people who are looking for somewhere between a month up to 2 years is typically what I've heard. So you really need the deployment to last the entire time of your deployment, right? So you need the CTD to last. And you can also think about how you want it to be collecting data. Again, with profiling data, it's usually you want to sample as quickly as possible to get as much data as possible. For more CTDs, I find you really want to maximize the sampling. So if you're out there for 2 years, you'll sample so that, you know, the batteries or the memory will last up to 2 years. You know, if you have enough battery for another like 3 months, like you might want to tweak it to get the most out of the deployment. And you can also think about things like bursting and averaging. So often we'll set instruments up for what we call continuous at RBR. So it's, you know, take a sample every once a second or every minute, every month, whatever it is. You can't do every month, but you know what I mean. But you can also do bursting or averaging. So you can do a burst instead of the instrument turning on for, you know, 1 minute. You could say turn on for 5 seconds and do that every minute. So you're getting more data. It might help with any like spikes in the data that you're seeing. The second thing is the number of units. Typically on a mooring line, you're deploying more than 1 instrument. So if you have multiple instruments, how easy is it to set them all up exactly the same? Is that doable? Is it doable in a short amount of time? So just thinking of that. And then power is always going to be a big question on buoys. Is there enough power for the CTD or other instruments for the whole length of the deployment? And finally, for the integrations, so the integration piece is actually at most companies called OEM. So that really means that we work directly with the manufacturers of the platform. So with the glider manufacturers or the float manufacturers, and we give them essentially just the sensor piece, and we work really closely with them. So when you're picking a CTD for a platform, you first want to make sure that the platform is right for you. So, if you're trying to find a glider, there might be like autonomy requirements, again, like how long can the mission go, depending on where you're trying to sample, or depth requirements. So we actually do integrate on a bunch of different platforms. Power is probably the most important piece from an integration piece. These are fully autonomous platforms, so they're not. Right now, I'm not aware of any of these platforms being able to get power from another source while they're out there. So having as low power on the sensors is really beneficial, because then it'll extend your deployments. So lower the power sensors, the longer the deployments. And again, these are fully autonomous systems, so they're out there by themselves with no way of getting more power. So typically, the lower the power, the better. And then, like, the size, these aren't huge pieces. You can see the scale here from Rutgers, that this is a glider and then this is a human. So there's sensors can't be gigantic to fit on here. Okay, so those are the considerations, like kind of the technical considerations for the different applications that I think of, again, profiling, moored, and integrations. So the next part is these other physical considerations. So I think the second question after how are you planning on deploying your CTD, like how are you trying to use it, is how deep, because the deeper options typically require metal, typically titanium, because plastic materials just can't withstand that kind of pressure. So that's something to think about, and make sure that you're deploying CTDs that are rated to, if it's rated to 200 meters, like send it to 200 meters, really make sure you're deploying them to the correct depth that they're rated to. Another, I call this a physical consideration, I guess, typically, is what other non-CTD parameters are you interested in? I've been talking solely about CTD so far today, but there are many other different types of sensors that people want to integrate now, and we're getting more and more requests for biological, chemical, and geological sensors. So, thinking of, say, in the bottom corner here, like a CTD with extra options to measure oxygen and turbidity or something. Having just a CTD is often great and awesome, but it's not always exactly what you need for your science question. And think about, do you need real-time or near real-time data transfer? And then that comes, you have to think about things like cables and connectors and how easy it is to integrate those things. And there's also ways to transfer data using different kinds of modems. And then environmental factors. So this includes, like, are you expecting biofouling? Are the currents really strong if it's on a mooring line? Do you have to worry about, maybe I should get a smaller CTD because it's lighter, there's less drag, how to make sure that it's really secure to the lines. And temperature is going to be a big thing for anything that's battery powered. So we saw a couple of examples of some polar work earlier, and often in those situations, especially for, let's say, the mooring line, you do need more batteries, because cold temperatures really affect battery life. So you need to consider that, and consider, if you are deploying it in ice or freezing conditions, like, will the sensors still work? And then I call these the extra considerations. Again, I didn't really know what else to call them. They're just other things to think about. One is, how good is the CTD? And that might seem silly, but I think it's a really important thing. If you think about the specifications, like the accuracy, the resolution, and the stability of the sensors, that's really important. And I'm going to get into that a little bit more, but you could tick a lot of the boxes, like the fast sampling, and that might be fine. Or, for example, you have a CTD that will last for, your whole 5-year mooring campaign. But, depending on the stability or the drift of the sensors, what is that data going to look like in 5 years? Calibration turnaround is a big one we hear a lot about. Like, what is the cost of not having your instruments in the water? How much of a cost to you for your science is not having it in, if you have to pull your instruments out and wait a few months to get your instrument back? And the ease of use, like, do you need to be very, very qualified and especially trained in ocean technology to be able to operate these systems, or can you teach somebody how to use them in a quick a couple of hours. And the consumables are typically things like the batteries and the O-rings, so the things that wear out over time. You want to think about, like, are they common to get or are they proprietary? So do you have to go back to the manufacturer to get them? And if so, if not, still to think about, like, can the user replace them, or does it have to be something that has to go back to the factory to get done there? So that's something to think about. So this is like, these aren't physical things or CTD feature related. This is more about the actual, like, manufacturer itself and how it, again, deals with calibration and, like, use pieces. And these, I find, have folks don't think about these as much. People do ask, like, what's the maintenance schedule, so they can put that into their budget, but there's other pieces to think about. That is a cost. There is a cost to this as well. So the good CTD part, I put that in quotes because there's lots of CTDs out there. So the three specifications I like to think about is the accuracy. So that's essentially how close to the truth is the measurement. So I don't know. Pressure is probably my favorite parameter. I don't know what that means, but if you have a pressure sensor that's saying, okay, I'm at 100 meters, or sorry, if you actually are at 100 meters, what is it actually reporting? Is it reporting 99 meters or 101 meters? Kind of what's the range if it's actually at 100? So how truthful essentially is the CTD? The resolution is how much of a change can it detect? So again, think about pressure, like, can you see surface changes? If there's if there's a big tidal range in a particular area, probably most CTDs will see that. But if there's small surface changes, will that be seen by the CTD? And the stability, I think the stability is talked about the least, but I think it's very important as well. It's typically a unit over a period of time, which sounds jargony, but basically it's like X degrees Celsius over a year or X degrees Celsius over a month. So basically it's how it's over that period of time is that you can kind of trust that the accuracy is going to be the same over that period of time. A good rule of thumb is that a good stability spec is that it's the initial accuracy, so the accuracy per year. So if it's per month, that's a little bit, that's 12 times worse than having that accuracy per year. So, and that's important because of the calibration piece. So if you need an accuracy of, whatever, 1 degree Celsius, and the stability is 0.5 degree Celsius per year, then now every year you're expecting to lose 0.5 degrees of accuracy before it needs to be recalibrated. So really the stability is an important piece for how often you need or you should be recalibrating. So really what I'm talking about here in this last bit is, like, the quote price, the price that you get on your quote is not the bottom line price. There are other things that you should be thinking about, and that the price is really a more holistic view of many different factors. So now I'm going to talk explicitly about profiling CTDs at RBR, moored CTDs at RBR, and integration OEM CTDs at RBR. So this is a very common CTD. It's called the RBR Concerto CTD. This is the C, the conductivity cell, is this red here. The T is this, it's called the thermistor. It measures temperature. It's right here. And then this is the pressure sensor. So how do RBR CTDs capture this structure that I talked about earlier with the thermoclines, the pycnocline, and the halocline? First, we have up to 32 Hertz sampling in the CTD variants, and the sensors have a fast time constant. So between the three, conductivity, temperature, and depth, or conductivity, temperature, and pressure, the limiting factor in terms of time constant is the thermistor. So we have a thermistor that has a 0.1 second time constant. Our standard thermistor is 1 second. So this means that now when you're profiling the water, the sensor is actually responding at 0.1 seconds. And the other two sensors, conductivity and temperature, they're essentially instantaneous, but like I said, the temperature is really the limiting factor there. So these are fast sampling. You can see here, if I point out on this concerto, this is a thicker thermistor, and on this concerto over here, you can see it's a thinner one. So this is the fast, and then this is the standard. So the Wi-Fi piece, so it doesn't always have to be Wi-Fi, but for us it is that, that sanity check of checking the data, while you're out in the field. Did I capture that feature? We do have Wi-Fi enabled on all the CTDs, and you need to make sure that you tell, if you are going to buy one, your salesperson that you're interested in that, because it is something that needs to be turned on. And you can check the data on the spot, like I said, and we have a free Ruskin mobile app. You can actually use the app or a computer to check it. It doesn't really matter, but it's a great way when you're in the field to have that sanity check of, did I capture the thermocline? And then the enough data piece, using Ruskin, the desktop version, you can download it right now today, and you can play around without a CTD to do a whole bunch of different calculations by simulating an instrument. And there is plenty of autonomy through batteries and the space of the data piece. So I did run a quick check, and for say this instrument here, the concerto, if you did run it at 32 Hertz, it would be 19 days of autonomy. So the memory would fill up after 19 days, and that's if you're sampling 24/7. So every single day, around the clock, 32 samples of CTD every single second. So that is quite a while. So again, when you're out in the field, if you're going out for a day, you have something like that, you don't really have to worry about, will I have enough memory or batteries to get through this deployment? Okay. So moored CTDs at RBR, this looks very similar to the first one I showed you. A few differences. This is titanium, so it's a deeper one. You can see this is a thicker thermistor. It's meant for moorings, and we have some connector back here. So the deployment length for moored CTD, again, I went to Ruskin and ran a simulation, and sampling once every 6 seconds on a CTD, concerto CTD, the battery will last about 2 years, just over 2 years. So again, you can go into Ruskin and tweak around these factors to maximize. I didn't do the bursting or the averaging I talked about, but you could also go in there and tweak it to, again, if you know your deployment is going to be 2 years, then you can go in and tweak that until you get the right number of samples. The right sampling interval to maximize, the metadata you can get on the battery and the memory. The number of units. So we actually have quantity discounts for when you buy multiple instruments, if you are setting up a mooring line that has many, many instruments. And we have this awesome feature in Ruskin, which essentially lets you plug in one instrument, you configure it, and then without touching a button, and you're just unplugging and plugging in, you can configure a whole series of instruments to deploy exactly the same way. Typically on mooring lines, you want everything to be sampling at the same rate and the same time so that you can sync up the data later. Oh, and that feature is also really powerful for when you recover the instruments, and you can automatically as soon as Ruskin sees that you're plugged in, it'll download all the data, stop the deployment, so that it can be very efficient to set up and recover the instruments. And then the power, I always say that power should never be a problem with your RBR instrument, because we have so many options for external power. It could be something like this, where there's a connector and you're feeding in your own power. We have external battery packs like the RBR Fermata that you can use to power the instruments. And then we also have I say internal, but it's really doubling the length of the concerto by having this really be second housing that doubles the batteries. So you're really doubling the deployment. So it's not fully separate. There's not a cable. You can just connect it on directly. So power should never be an issue for these sorts of deployments if you're using an RBR CTD. Okay. The OEM or the integration CTDs at RBR. So this is 2 different variants of our glider CTD. So we actually manufacture CTDs for many different float and glider manufacturers. We try to standardize it as much as possible, but they do have slight differences. For example, this is again our RBR Legato, which is for gliders. and its pressure rating is down to 1,000 meters or 1,200 meters. So if you need something deeper on your glider, you might need something like this, which is called the RBR Centauro. So it's better for deeper applications. So there, again, we try to standardize a lot of pieces, but they're all very much specified for the float manufacturers typically, and we have really great relationships with them to make sure that things fit power-wise and size-wise. So the power from RBR CTDs is often multiple times lower in power than the status quo. So that's one thing to think about to really extend missions on these autonomous platforms like gliders and floats. The power is a little bit shocking, I think, to people who don't know RBR instruments. So like I mentioned earlier, 19 days if you're sampling around the clock at 32 hertz for just a few batteries inside, essentially. So these are super low power. And the size, like we actually designed these specifically with the size of these platforms in mind, like particularly, for example, again, the Legato, there was a particular bay, science bay that, had to fit that in. So it was built around kind of that specification. Okay, so the physical considerations that I talked about earlier, like the depth. So we have CTD options down to 6,000 meters. Our shallow version is around 750. So this is, say, our shallow CTD here. I say shallow in quotes because for some people, shallow is 20 meters or 50 meters, or the shelf break. So again, you don't want to take something that's rated to 750 and try to see if it'll go to 1,000 meters. Please deploy your instruments to where they're meant to go to. If you do have something that's 6,000 meters, if you try to deploy it in 100 meters of water, I'll talk about that in a little bit, but it'll still measure things. Maybe the pressure or the depth ratings won't be as high resolution or high accuracy as you'd like. So really pick the right. One question I ask is, how deep are you going, or what's the deepest you'll go? We have a lot of options for non-CTD parameters. You can get up to 10 parameters on one instrument. It's called the RBR Maestro. Outside of CTD, the most common things we've been asked to integrate are oxygen, chlorophyll, and turbidity. There's many other things. Just ask us if we do integrations. And there's a few of these sensors here. This one measures light and radiation. This is oxygen, and this is FDOM, turbidity, and chlorophyll. And then you can get them integrated on here like this. And then thinking about the real time or the near real time, we have options for mooring line modem, which is, again, very at the beginning of the talk, the folks that are deploying it through a hole on a mooring line that all the instruments are going to be frozen in. The data is coming up the actual mooring line itself. It's called a jacketed wire. So the data gets transferred up there using modems. You can use like external connectors and cables. We do have those options. Again, just think about, again, talk to your sales rep about like what's going to work best, because there's a limit to kind of the length of the cable and like how fast the data can be transferred and everything. And then you can also use the Wi-Fi that I mentioned earlier as a data transfer piece. You can get the data off of the instrument without opening it up and download it and then share it, on Dropbox or whatever. And then the environmental factors. So I mentioned biofouling. So for our optical sensors, like these three at the top, we have wiper options. But for our CTD, we're hopefully later this year, we're going to be introducing an anti-fouling solution for our CTDs. Again, the second point here was about mooring line movement, or if there's a lot of like currents and stuff like that, we have clamps that you can use onto the line. So again, you kind of want to think about that, like the dynamics of where you're deploying it and how many clamps you need or how much backup tape you want to use. And RBR CTDs are well known for operating well in cold climate conditions. So if you freeze the CTD in, it works just as well than when it's thawed out. But again, the one thing to remember is that you have to consider the temperature piece. So again, if it's really cold, it's going to drain the batteries a little bit more. So when you're doing your planning, you want to maybe like say cut half the battery life. So it says 100 days, say actually that's 50 days because I'm deploying it in cold waters or in the Arctic. Okay, so these extra considerations I talked about as well. How good is the CTD, the accuracy, the resolution, and the stability? So we have conductivity, pressure, and conductivity, temperature, and pressure, and then accuracy, resolution, and stability. I'm going to focus on pressure just for the sake of time. I'm not going to go through it all, but essentially most pressure, most manufacturers talk about pressure as a full scale. So this means the calibration of the pressure sensor. So again, I was earlier talking about a 100-meter pressure sensor, so I'm going to stick there. So if you have a pressure sensor good to 100 meters, that means for this 0.05% that the accuracy is around 0.05 meters. So if the CTD is exactly at 100 meters, the CTD from RBR will tell you that we'll give you a number somewhere between 99.95 and 100.05. So very small, a very good accuracy to have that small of a change. And then the shallower the sensor, the better the accuracy, the better the resolution for the pressure sensors. The other things are the standard across all pressure ranges. And then the resolution, again, that's like how much surface change can I see? This is about a millimeter. And then the stability is the initial accuracy per year, as you can see. So again, every year you can expect that your pressure measurement is going to be off by 0.05 meters if you're not getting it calibrated. And because all of our stability specs are per year, that's actually how often we recommend you getting your CTD calibrated to bring it back to that factory level the very first time that you get it. We recommend that, but also you have to think about your science and what's going to work best for you. So, maybe you don't need as high the accuracy, and then you can get your CTD calibrated every 2 years because you're okay with, a drift after 2 years of, 0.1 meters. So speaking of calibration, our calibration turnaround, we have fast response from our support team, and currently we're doing something called a 3-year free calibration guarantee. So you can get your CTD calibrated at RBR in 3 weeks. There's some caveats and things, but that's basically it, that you can get it done in 3 weeks. So that's not months of having your instrument out of the water. If you are going to get your CTD calibrated soon, just let the team know if you have a tight timeline, and we often try to do what we can to really fit it in around your deployment. Of course, if you say I need it calibrated in 2 days, that might be a problem. So just give us lots of heads up. The ease of use part, our CTDs are literally shipped with twist activation enabled, and that sounds very weird, but essentially what it is the CTD, you get it, you open the box up, and you just twist the end cap, and now it is collecting data at whatever the sample rate you chose. So it's very, very easy to use. You don't need to be, a super expert in CTDs or ocean tech or an engineer to use them. They're very easy to use. And the consumables, again, those are the pieces that you have to change probably every time, or every time you go in the field, you at least have to check them. There are 3 consumables on an RBR CTD: the batteries, which are actually AA batteries, the desiccant, which is the thing that soaks up the moisture, like the little silica packets you get if you buy a new bag or a new purse, and the O-rings, which are included sort of with the order. The spare ones are. So these are all user replaceable. You can buy the AA batteries anywhere. The desiccant are rechargeable, so you can bring them back to life yourself. And and then the O-rings, you can always order more if need be. Okay. So again, I mentioned earlier that the quote price is not the bottom line price. There's other things to consider about the cost. Of course, the cost of the instrument is a piece of this, but the cost is also how often you need to go and recover and swap instruments out to answer your scientific question, right? So again, this is going back to how good is the CTD? If the specs aren't, if you need something that has 0.5 degrees Celsius accuracy and it's drifting by that amount, every month, you have to go out every month to change it around. So having high quality specifications in terms of like the accuracy and everything, that probably means you can leave your instruments in the water a little bit longer. The cost of getting the instruments out of the water, again, the calibration turnaround time. So if you can leave your instruments in the water for a year or two, that's probably going to save you a lot of money for going out and doing recovery. The cost of a highly qualified personnel to operate. So this is speaking to the ease of use piece. So, you know, is it really easy to set it up? Like, how long does it take to learn how to use it? You know, are there lots of like different moving parts and pieces that you have to kind of figure out? And the cost of the consumables. So again, like if the consumables aren't user replaceable, that means that the CTD has to go back to the factory, or if the consumables are proprietary, so that means that that it has to be replaced there. Like, how much is that going to cost? Sorry, I'm just being conscious of the time because we only have 15 minutes left. This is the summary. We're getting pretty close. So not all CTDs are ideal for the same applications. So for profiling CTDs, you really want to think about fast sensors with fast sampling. Ideally, it has a quick check feature like an app, Wi-Fi to like check, did I get it? The instrument needs to be able to handle the data, which is, again, like, will it be able to hold all the measurements? Will the batteries last while I'm out there? For more deployments, you really, again, it sounds so silly to say it, but it's true. You really need the CTD to last for the length of your deployment and to collect the data that you need to capture, you know, again, to answer the science question, thinking about how easy it is going to be to set everything up. I love how easy it is to set up many RBR instruments to be able to easily deploy and recover. Again, power is a big thing that you have to think about for these sorts of deployments. And then integration piece. Again, make sure that the platform is right for you. That's a good initial question. And you know, again, for the CTD parts, it's, or sensors in general, you know, that they're the right size and the right power for the platform. The physical considerations, again, make sure you're deploying to the correct depth. Think about if you need other non-CTD parameters like chlorophyll or oxygen and how that might you know, elevate the project that you're working on. If you need real time or near real time, you know, you need a connector or a way to send data to a surface and get the data off. And then the environmental factors, again, want to think about biofouling and, you know, if it's very dynamic, you know, how are you going to ensure that the CTDs are on there? And those like extra considerations that we just spent a bit of time on, like how good is the CTD, how long does the calibration take, how easy is it to use, and you know, how to deal with the consumables. Can you deal with it? Does it mean that the instrument has to go back into the factory? Okay, I'm going to stop there. Thank you. If you feel more confused than ever, because that was a lot very fast, always write to us. This is not just, I'm the only person who knows this. Your sales rep will definitely know how to walk you through the CTD options. I just wanted to give you some things to think about before you sort of pick a CTD. So all the different components all together. But again, just going back to the application, like how are you trying to put the CTD in the water? That will answer a lot of our questions to get you down the right road to get exactly what you need to make sure that your deployment is successful. Okay, I'm going to check the chat. Okay. Okay, great. So a question which I mentioned earlier is pretty common that we get is the maintenance piece. Like, how much maintenance does an RBR CTD require? And there's really two pieces I think about. The first is the kind of general maintenance for when you're going out. So those three things I mentioned earlier, those consumables, the battery, the desiccant, and the O-rings. Every time you deploy, you should check all three. Because the batteries, if you don't have enough juice, it's not going to last for your deployment. The O-rings, super important, because if they leak, your instrument's destroyed. And then the desiccant actually keeps the inside of your lager dry so that, you know, when you close it up, you know, there's condensation inside, so it soaks it up. So if it's spent, you could get corrosion inside, and then that will actually affect your battery life. So, so those three things, the O-rings, the desiccant, the batteries, every time you deploy, you should check those things. So that's like one maintenance piece. And the second thing I would say is get your CTD calibrated every year. That's the other piece, because when we get your CTD in-house, it's not just sent exactly to the Cal lab and that's it. Our service technicians actually take it and do a whole process of checks on the instrument to make sure that everything is up to snuff. So they check things like the sleep current. So if there was corrosion that you didn't see, now they're checking it. Oh, there's actually corrosion on this logger. They haven't been changing their desiccant. So now when you get the instrument back, support will reach out to make sure that, to tell you what's going on essentially and say like, okay, you have corrosion, we need to fix this or replace it. So other than that, there's no main maintenance things. Keep your CTD clean. Again, I mentioned biofouling earlier. This conductivity cell is susceptible to biofouling. But if you keep, you can go out and service it and keep it clean, but with the battery life being what it is and the memory being what it is, there's not a lot of like hardcore maintenance to it. If you are cleaning the CTD, we have suggestions on our doc site that will tell you. So I think it's, we can send the link to that. So it just tells you like, if you're doing this, if there's a lot of like growth on there, you can use a vinegar bath and such things, but these are very robust sensors. So there's not a lot of maintenance. So to circle back and answer the question, check the consumables, which are the batteries, the O-rings, and the desiccant before every deployment, replace as needed, and get your CTD calibrated every year, because in addition to getting, the very best quality data again, now you're also getting this like in-house, like again, sanity check, like is the CTD working right? So that's what I would recommend. I'm just looking at the other questions. Okay, so Kelsey is asking, what determines how quickly a profiling CTD needs to go through the water? So, and Kelsey, you can just like pop in if I'm answering the question, right? I think there are two things to think about when you're profiling. One is, like I mentioned, the actual response time, or not the response time, sorry, how fast the sensors are taking data. So we can do like 32 hertz, that's one thing. The second thing is how fast the CTD is going through the water. So typically, when instruments are in free fall, RBR instruments, depending on what kind of instrument it is, so the smaller ones, there's less weight, so they fall through the water more slowly. If you have a cage, that's going to add weight, it'll move a bit faster. Typically, I'm guessing you'll see a fall rate between 0.5 meters a second and 1 meter a second. So if you're falling at 0.5 meters a second, and you want, 16 data points every meter, then you can sample at 8 hertz. If you're going 1 meter a second, you need to get those same data points at 16 hertz. So really it comes down to your scientific question. Like if you have a very, very sharp thermocline that you're trying to see, you're going to want to sample as fast as you can through that and go relatively slow through that if the thermocline is changing very quickly. And some places have like tanks set up that, that like it's super, super stratified. So you can kind of test that out a little bit at some facilities. So those are kind of the two things. Now, the winch part, we're actually later this year releasing a winch here at RBR that like spits out the line so that you can measure while the boat is moving. And that's another piece. So if the boat is moving really fast, the line needs to be spitting out really fast. If the boat is moving slower, you have to spit out the line a little bit slower. So it's a combination of a few things, but typically how fast the CTD can sample, how fast the CTD is falling through the water. So those are two things you really want to think about. And then that will answer your question of how fast does the line need to spit out. And if you have a boat that's moving, that's a whole other piece in there. But again, it's those pieces. But I would strongly recommend you go back to your science question of like, I don't know about you, but when I was in grad school, the region that I studied in was already well studied. So we kind of knew what to expect. So if there was a really sharp thermocline and we were seeing it, we kind of knew what level of CTD sampling we needed. I hope that answered your question, Kelsey. So have we studied the free fall speed of our CTDs through the water? If so, is there an average number? So I think those like ballpark figures I gave, 0.5 meter a second or a meter a second, are common. Like we haven't, because people are using them in all different ways. Earlier, I showed a picture of our research scientist, Matt Dever, and he had a winch, and you can see him like holding it out. You can see a little bit of the RBR CTD cell at the bottom, but he, during his time at Hui, helped develop this basically collar that goes around to make the CTD fall through the water faster, up to 4 meters a second underway. So you can add weight. Again, reach out to us about how that's best done, but because there's just some proximity effects around the connectivity cell that need to be considered. So if you need faster or slower, like we can kind of give you some recommendations for that. So Kelsey's asking again about the profiling speeds. So so I should have mentioned this. There's just so much information. Sorry. The winch. So typically when you're profiling, let's say you're doing a winch. So you're profiling the CTD down and you're pulling it back up. The undisturbed water is actually on the way down. So we face our CTDs down essentially, and then as you're pulling it back up, usually people don't use that pulling back up data because the CTD sensors are all here, and then you're pulling it through the water, so you're disturbing all of your structure. So if you are measuring a thermocline, it might be really hard to see it on the way back up. Whereas if it's going down, it's measuring this undisturbed water, so you're getting all those features. So typically the payout speed is more important to like get it down to get like a really nice profile. But when Matt's been testing our new winch, he loves the speed on the way back because it's saving so much time. So if you have a really slow payback speed, like pay-in speed, it can be kind of a pain because you're losing precious sampling time. So our winch will like be paying out and paying in at similar rates. I don't know if it's exactly the same rate, of course, because there's safety things. You don't want like the thing like zooming back in. So I would say the direction that the most undisturbed water is the most important for like the sampling rate. So on the wire walker, it actually, the way it works, it ratchets down and a lever is released and then it profiles upward. So it has a clean profile on the way up. So the fast sampling is important for that. Again, there's so many pieces to all this, but the wire walker or our CTDs actually have this cool feature where you can like profile fast in one direction and slower in another direction, which is really cool. Keith, can you also see the question? I just want to make sure I'm not missing any. I'm answering them in order-ish links. So Keith did put the link to the doc site on there. Okay. So there's a question about thermal shedding if the instrument was in sunlight for a while, say on the deck, and then you're putting it in cold water. So again, I have recommendations for this. So first of all, let's say you're on a typical, beautiful summer for you cruise. So you're going out, the CTD is on the deck, and then it's in the sunlight. Now, like the conductivity cell is like 25 degrees Celsius, and you put it in the water, and the surface water is like 20 degrees Celsius. So we recommend a little bit of a soak at the surface to kind of get that the thermal mass, because as you can see here, this is a piece of plastic, so it kind of has to heat up or cool down. So if there's a big temperature differential, then you want to leave it in the water for the CTD to heat up or cool down. Some of our customers in the Arctic do a really cool thing, because as you can imagine, up there, the air temperature can be very, very cold, like minus 25 degrees Celsius. And then the water is going to be at the coldest, -5, because that's kind of around where salt water freezes. So for that's a huge jump. So then I recommend people getting cooler like a cooler that you would take, to the beach in the summer, and you put your CTD in there with like 0-degree water, like cold to us touching water, but then you can put it in there and then keep it closer to the temperature so you have less of a sit time. The upcast, the warm body will affect the temperature. So again, if you soak it at the surface, if you soak it at the surface in time, the CTD will sort of acclimatize and kind of bring up that the temperature will be, cooled down or heated up as much as it needs. For the upcast, it depends on if you're using it on like a wire walker, the upcast, the sensors are facing up. I don't know if people see much effect of like the body's a little bit warmer and you're pulling it through. I think that the data quality piece of like, if you're profiling down and then pulling it back up, people aren't really using that data on the way back up because it's not measuring undisturbed water. I don't see any more questions. Keith is going to launch the poll now. I know it's really close. Oh, it's on the hour. There we go. You can answer the questions. Sorry, we're right on the hour. If you have more questions, I'm going to move this poll out of the way a little bit. You can email info@rbr-global.com. My direct email is my first name dot my last name @rbr-global.com. Feel free to take a screenshot or whatever. There's a couple of poll questions there, which would be great if you can answer. And again, we will be in touch with the link to this and some of the Q&A answers and that cool infographic. I cannot vote for this poll. That's not fun. I mean, it is kind of fun still. I mean, I'm glad you are answering, but it would be fun for me to see the coolest way if CTD has been deployed. I've had people ask too about like, and I almost put it in, but I actually haven't heard somebody do it, like from drones and like dipping it into the surface. That might be interesting to try to do that to get surface stuff, but it's like, depending on the size of the drone, it might be relatively heavy, even though our CTDs are pretty small, like this one, the Brevio. And I think also when you answer these poll questions, if there's something like really cool, we can throw that into the follow-up email as well. There might be other things. And again, if you have other thoughts about CTDs, feel free to throw it into the chat. Oh, awesome. Okay, so if you're still here, we are sharing the poll answers. I think you should be able to see that on your screen. Looks like most people go to the vendor websites to decide on selecting instruments. That's really interesting. Cool. And the reason I'm saying that's interesting is because I often think that you ask your colleagues. That's cool. And then price often seems to be the most important thing when selecting a CTD. Okay. I'm going to call it. Sorry that we're 3 minutes over. Maybe next time I should start on time. We'll be 3 minutes over. Thank you all for attending. Again, contact details there. We'll be in touch.